Well, group, hey, it's Mr. Black. Hope all is well here in my little home studio. This is going to be the last little bit of new information for our study of stellar evolution. There'll be no more new information after this week's attendance check and our little grid of assignments. Hopefully you're keeping up. I'll just want to let you know that we're going to kind of finish up with a test, quiz, midterm, whatever you want to call it. And I'll give you some more information and give you a little study guide for that. Hopefully you're going to pass the fourth quarter. That's my hope. That's my prayer. That's what I'd like to see happen. I've got some slides here, and I want to take a look here. We've got the Hertzsprung-Russell diagram. Astronomers call it the HR diagram, but it's very important. You've got to be exposed to it. You have to be able to understand it. It was independently discovered by two different astronomers, one American, one Dutch, that stars are basically developed, they go through a life cycle based on their brightness. That's luminosity. That's the y-axis on the left there. And that, of course, the higher the number, the brighter the star, the lower the absolute magnitude. We've learned that last week. We'll also be putting a key for the black hole questions and for the stellar distances and magnitudes. I'll put that up in the next study guide. This is the life cycle. Every star in the sky falls somewhere on the HR diagram. If you look down on the x-axis, that's temperature. Obviously blue is a hotter color than red, and so these are the hotter, put out more heat, 30,000 K all the way down to 3,000. So red are the cooler stars. So brightness and then temperature for our x-axis. Every star is on here. Of course, once they die, meaning they go supernova and into a neutron star or black hole, or if they just fade away into a planetary nebula, white dwarf, and then of course a black cold dwarf, they're off the HR diagram. So this is for that life cycle. We're going to find out once again, make sure you got this, mass is the most important thing in the stellar life cycle. The bigger, more massive OB type stars like Spica and those types don't live as long as the lower mass stars like our sun. Okay. The main sequence is that little strip you always see kind of going right through any diagram of the HR diagram. That's where the main fusion reaction is hydrogen to helium. That's the bread and butter of any stellar nuclear fusion reaction. And that's, when you're on the main sequence, that's your most common fusion product. That makes the star blue, white, or yellow. Once it starts going orange to red, then it leaves the main sequence and then goes into the giants or the red supergiants, which means you're going to eventually go supernova. See the bottom left down there? That's your white dwarfs. They're really hot, but they're really dim because they've been compacted, like Neil deGrasse Tyson said, into a souffle of carbon, hot carbon atoms, right? That black or that white dwarf that's going to cool to a white dwarf. Well, let's kind of get this into the life cycle. So the low mass stars, which would include our sun, and that X at the top of this slide, the 0.5 to 4X. X, of course, is one solar max. It's our yardstick for the mass of a star. So these are the low mass stars. We know that they form out of a nebula into a protostar. They start out as white to yellow main sequence stars. They go red giant. That's when they basically run out of hydrogen and they're fusing helium and heavier elements. Then they just run out of gas, become a planetary nebula, and then they cool down. They don't really cool down for a long time. It takes a long time for all that heat to dissipate, but they go from a white dwarf. You can see them going to the bottom left part of that HR diagram. This pathway, it's very important. Make sure UA students get this. This pathway takes billions of years. Okay, this is a slow process, a long stellar evolution. This is where we think these low mass stars are where we're going to find life, if we're going to find it out there in the cosmos, is around the low mass stars, because life as we know it here on Earth needs hundreds of millions, if not billions of years to evolve into something that can watch a YouTube video and learn from it. Okay. Um, so here's once again your low mass life cycle from protostar to white dwarf. Then you get a star, and this varies. I still teach 4x to 19x. There's some debate. Some astronomers think a 16, 17x star can the supernova can form a black hole. There's still more research to do on this, but I think we're real safe by saying a star that's 4 to 19 times the mass of our sun, what we call a massive star, is going to end up from the supernova crushing that core down, that iron core down to just pure neutrons, chargeless neutrons. It's very dense. That puts out the radio waves. We've studied that. This pathway takes hundreds of millions of years. Now remember, that's the difference between billions. I mean, there's some decimal places there. So these stars, we don't think around the larger stars, the Denebs out there, the Siriuses, all those big stars. We don't really think life is really going to evolve into something that we'd all be proud of. You know, who knows if you're proud of algae or bacteria or viruses? Are you kidding me? But and then of course our life cycle of supermassive stars. These are 20 times the mass of our sun. We know that these are going to go supernova, and those are going to crush down a hole in the fabric of space-time. So here's your 20x. Now these only last for tens of millions of years on the HR diagram. The bigger they are, the hotter they are, the faster the fusion occurs in the core, and the faster they run out of the hydrogen and begin that death spiral into the red supergiant. Then they go supernova. See the big S word, super, in there, ending up as a black hole. And, you know, I did a lot, gave you a 30-minute presentation on black holes last time, and we're going to actually solve for that. It's going to really, it's part of this course, and it's part of any astronomy course, is to actually crush a star down into a black hole. So just in conclusion, based on the luminosity, the brightness, these are low numbers, but very bright. These are hot, so this would be a hot, bright star. These blue giants, these are the O types. They're very rare. These are 60 or so times, 30 times. We've got some big Spica, Beta Centauri, some giant stars. So you can classify them O, B, A, F, G, K, M based on temperature and brightness. Okay. These blue supergiants like Spica have a very short life cycle. We're not looking for life around Spica in the constellation Virgo. And by the way, we're getting close to May. Get out there. Watch Spica in Virgo rise in the east. And that should, all you farmers, get out, plant your crops. It's springtime. It's getting ready to go. Well, all right, let's pull out our calculators. This is what I mentioned in that little film that I produced, and I haven't really heard whether or not you liked it or not. I was hoping for more animations and more movie clips than what I produced, but oh well. So here we have Hawking's famous equation, the formula used to determine if a mass is crushed down to the radius of an event horizon. Event horizon means to escape it, you got to go faster than light. And we know we can't go faster than light. So nothing's going to escape it. Not you, not a radio wave, not a microwave, not light. It's the black hole. Schwarzchild radius, the equation is 2gm over the speed of light squared. And these units are small. Okay, they're small units because it's going to get crushed down to a way smaller size than the star was originally. The gravitational constant by Hawking's was, this is from Newton, but this is a small, instead of a Newton, this is a little like the size of a little die, like a little bitty cube. So it's 6.67 times 10 to the negative 8th centimeters squared per gram squared. Don't get caught up on the units, but do realize that we're looking at things on a small scale. Speed of light, I've converted it for you from kilometers per second, which would be 3 times 10 to the 5th, to 3 times 10 to the 10th. Okay, that's the same number. It's just a different unit. A whole lot of centimeters every second that light's traveling. Now, the mass of the star is usually given in kilograms, and all you do is just move the decimal 3 to get to grams. Not a big deal there. Note the units are small because supernova crushes the giant star core into a very small singularity. Um, Once we get the radius, the Schwarzchild radius, named after Karl Schwarzchild, the great German astronomer who died during World War I, then we can solve for the volume. How much space is that black hole taking up? And you can imagine it's not going to be very big. So we're going to plug in the radius, cube it, times pi times 4, and divide by 3. Once we have volume, we can take the mass, the original mass, divided by the volume, and we can figure out how dense it is. Do you think a black hole is going to be dense? I think it will be, right? You get crushed down by a supernova and you would be really dense as well. And remember too, anything could be crushed down to a black hole given enough force. The only force we know of is the supernova. So it can only happen to these massive 4x and greater stars bigger than the Earth. So you can see I've solved it here. I took r equals 2, because it's 2 dimensions, times g, 6.67 times 10 to the negative 8th, times the mass of the sun. This is crushing our sun. We're going to take our sun and make it a black hole. Okay? We're going to divide by 3 times 10 to the 10th centimeters the second squared. You always square the speed of light unless you want to tangle with Einstein mathematically. Most people aren't on that level yet. So let's go ahead and square our speed of light. If you solve for this, I'd like for you to do it. You come up with 293,480 centimeters, and we move the decimal 5 from centimeters to kilometers is 5 places, and we end up with 2.93 kilometers. Are you kidding me? We crush our sun down to a black hole, the event horizon is only going to be 2.93 kilometers. That's really small on a stellar scale. Now I'm going to take that in centimeters, cube it, times pi, times 4, divide the whole mess by 3, and I get the volume of the event horizon. This whole area is 1 times 10 to the 17th centimeters cubed. Sounds big until you figure out that the actual, I put it at the bottom here, the volume of the sun is 1.41 times 10 to the 23rd. So we really made it small. Now density, this is where these black holes are the densest things we know of. They're denser than a freshman's cranium. And that density, mass, it's the original mass, 1.98 times 10 to the 33rd grams, divided by the volume. We solve for it. We come up with the density of that black hole is 1.87 times 10 to the 16th. That is, my dear friends, denser than anything we could ever dream of. Okay? So that's how you would solve. I'm going to post a couple more practice problems. UA students are going to be able to do that for the midterm. And the midterm is going to be more like a quiz, but we will have to do it. If you want credit for fourth quarter astronomy, you're going to have to show me some work. It's good to see you guys. I haven't posted a Zoom yet. I haven't heard anybody crying for a Zoom. If you're crying for a Zoom after this, let me know. Get your calculator out. I've got one right here in my home studio. And I tell you what, with that, I say let's go ahead and call this good. And let me hear from you. Make sure you get your homework turned in. I'm going to post this after the homework is due tomorrow at 2 p.m. Okay. Bye, everybody.